preferably if you can turn on your mic, it will be much easier for me to understand instead of reading comments from the chat. So much easier, okay? Now, today is a very significant and important chapter because function is one of the key things that in most cases software engineer will use functions quite a lot, okay? So it is very often that, it is common that software engineering students would use functions in programming, but understanding function and mapping is quite important. We're looking at the mathematical element of functions. It's a little bit different, but not so different because it uses, the moment you understand the mathematical concept, applying in the computing world is not so different, okay? So basically what are functions? A function f from a set A to a set B is an assignment of exactly, this is just an important, if you have the slides, this is one of the key things that you would want to highlight, exactly one element of B to each. Okay, yes, we had to complete the Warshall algorithm. Yes, you're right. Let me just do that. Completely forgot this one. Just look for the lecture notes and do the Warshall thing. Okay, so thank you for reminding me about the water. I completely forgot about this. Sorry about that. Now, we're still on the, before we drop into the new topic, relations. One thing that we need to figure out is that, if you recall, we were talking about transitive closure. Just change that, got it. We're talking about transitive closure, and you will see that when you do the Boolean product, you are able to achieve transitive closure if you do the Boolean product of a relation. So r squared, r cubed to the power of 4, and so on and so forth, depending how many elements you have in A, right? If you have n elements, that would be to the power of n, okay? So the transitive closure is, this method of transitive closure can be a little bit tricky, especially if you have many elements, and implementing such algorithm, if you implement such an algorithm in a computer to do that, well, it's not a straightforward procedure. That's why they came up with something called the Warshall algorithm, which is used in the computing world to find transitive closure. In simple terms, when you have an XY and you have a YZ, how do I find the link between XZ? Now, this Warshall algorithm is something which is very much used into graph problems. Whenever you're trying to figure out what is, could be routes, if you're designing road networks, if you're designing railway networks, if you're designing anything, it could be a network, a real life network, data communication network, and so on and so forth. So this is a very important algorithm that could simplify so many things in as far as graphs are concerned. And obviously it uses matrices to do that, right? The representation of matrix is very important. Just give me a second. I'm having a little issue delay here. I don't know if you can see that. Let me just close everything and get back to it. Just give me a second, please. 1 minute, please. Let me just solve this. Better now. Let me just share my screen now. Okay, so yes, so we're talking about the Warshall algorithm. The Warshall algorithm is a very common algorithm that is used to solve, as I said, graph problem, especially directed graph, which is a very good algorithm to find transitive closure. So here you can see if you were to have graph A, for example, there you go, start Studio Day again. If you have graph A, and then you need to find if somebody is able to get from 2 to 1 and 1 to 3, can I build a straight path from this one to this one? Okay. For instance, this is just an example of how to illustrate this. Okay. So can this be done this way? Okay. For instance. Okay. So again, the Warshall has been designed. I'll explain the algorithm. I'll explain it from a much simpler perspective of what the algorithm is actually doing. It's not difficult to understand it. It's not difficult at all to understand it, but I'll explain it in a much. Yeah, I'll explain the algorithm. Okay. Now, I want you to full attention on this one, okay? Because I'll simplify all of these. I'm sorry, I don't know why the computer is doing that, but I need your full attention on this to explain this whole concept of whether this one or this one will be applied, and I'll explain in details how this works. Now, what you need to know, suppose you have what it goes from, if you have closure, it will go from this being the R, and this being the transitive closure, the RT, right? So I'll skip all that and I'll go into the details of how this actually works, okay? So if you have a matrix, whatever be the size of that matrix, what you would want to do in that matrix would be something like this, right? So if you have 0, 1, 0, 1, 0, 0, and 0, 0, 0, what you will want to do is you will want to represent, you will want to draw rectangles or use a ruler. Do the first one, the first row, and the first column, right? And then once this is done, do the first row and the second column. And then once this is done, the next part would be do the first row and, no, sorry, I made a mistake here. Sorry. Do the first, let me just give you an example here. I made a mistake here. Okay, my apologies on this one. So do the first row and the first column. Once this is done, so first, if you have a 3 by 3, you want to do first row. I'm just going to row and column. You're going to do first row, first column. If you're going to, for the second one, it would be second row and second column. You need to do it 3 times, okay? Given that it is a 3 by 3. And the last one would be this one. Third row, third column. Right, so you're going to highlight all of these. Now, if you have, let's say, if you have a different situation here, if you have a 4 by 4, let's add a few more elements here. If you have a 4 by 4, let me just delete this one. It will do the same thing. So So now we have a 4 by 4. We will start with the first row, first column. So we will highlight the first row and the first column. There you go. So this is checked. Then we're going to do the second row and the second column. Check. Then we're going to do the third row and the third column. Checked. Given that it is a 4 by 4, we'll have to do the fourth row and the fourth column. Please, I'd like you to do this method of writing down the rows and the columns that you're currently doing. You check them once you're completed, just to avoid any mistake, because these are questions that will be above 10 marks, okay? And making a mistake on this one will have impacts there, okay? So far so good. Can I have feedback from you guys? Please don't send direct message, send to everyone. Feedback, please, on chat. Okay. Good. So let's move on now. Let's see how this whole algorithm will actually perform. So if you've understood this part, we will draw rectangles, right? And we will start with the first row, first column, second row, second column, and so on and so forth. Now, let's assume we have a 4 by 4. Okay, let's assume we have a 4 by 4. We'll start with the first one. I hope you can see my screen properly. We'll start, so we have a relation that has 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0. So that's our relation. That's R, okay? Sorry, I'm writing on this side, okay? So that's the relation R, okay? So we'll start with row 1, column 1, okay? So how it's gonna do, what the previous slide explains the algorithm, but I'm just gonna explain it as simple as possible. We will take, so you have two rectangles, row 1, so this is R1, and this is column 1, okay? And we will take all the values from, doesn't matter which one you're going to start. Let's say we'll take all the values from the column 1 and all the values from the row 1, and we will start comparing, okay? So basically, what we're going to do is we're going to take 0. 0 is on row 1, column 1, right? So we'll take 0 and we're going to compare it with itself. So it doesn't know there is no changes to this one. Well, then we will take 1 and we will compare it with 0 here. So we will take, if that is ABC, you can see it's written ABCD here, ABCD here. So we started with AA, then we'll take, whether you're taking this one, let's say I'm taking the column first, so that would be AB, and I'll take AB and I will check with BA. Then I'll take AC, then I will check with CA. Then I will take AD and I will check with DA. So everything from the column, the row A, and everything from the column, sorry about that, everything from the column A, okay? So row A, column A, okay? So put it into perspective. So I'm going to check for AB and BA, AB and BA. If both are 1, remember this, if both are 1, right, not one of them, if both are 1, then if this value is 0, this will become 1. So if AB and BA are 1, then I'm just going to put equal to here. Then sorry, I made a mistake here. This is AB and this is BA. Then BB should be 1. I repeat it again. If AB and BA are 1, then where both of them intersects, I used to draw a line here. Sorry about that. This and this, where it intersects here, right, which is BB, if that is 0, if that was 1 and that was 0, that would have become 1. Okay, now given that it is 0, it will, sorry about that. Given that it is 0, it will remain unchanged. So this is 0 and this is 1, so that will remain unchanged. So I will keep on going into that. So this is 0, so it will remain unchanged. Let me just check this one. This is 0, this is 0, this is 1. Here we're talking about AD is 1, and you're going to see that since AD is 1, if you check this one, right? If you check AD and DA, if you check AD and DA, you will see that if I draw a straight line here, you will see that if I do AD and DA, you will see that for, what is this one? DB, this should be 1, right? Given that both of them are 1, this is 1 and this is 1, this should be 1. So you're going to see that in the next iteration, this has changed to 1. Let me just explain it again in case there are any confusion, right? I'll just try to simplify it again. Let me just delete all that. So remember, we'll do the first row and the first column. So first row being oops, sorry about that, guys. Let me just do it here. First row, use a different color for you to be able to understand it. So first row, first column here, and first row is here, right? So what's going to happen is that if this is A, B, C, D, and this is A, B, C, D, so I'm going to check A with A. A is on itself. Then I'm going to check AB with versus BA. If AB is 1 and BA is 1, then BB should have been 1. Okay, but here it's not the case. Then I will check AB versus CB. AB, this one with this one. Now, given that this one is 0, CA, sorry, not CB, but CA. Sorry, CA, given that CA is 0, it will remain unchanged. Then I will check AB versus DA, AB versus DA with DA, right? Now, given that both are 1, then in that particular case, whether I call it DB or BD, Let me just call it dB. Right? Then dB, this one should equal to 1. Okay? So this is what you're going to see here. The amendment has been done in this one here. Okay? You can see that 1 has been added in here. So let me just proceed so that you can understand. So this does not stop here. So you have done for this one. If there was a 1 here, you need to do the same thing. You check this one with this one with this one with this. Then you check this one with this one with this one with this one. Okay, so I hope you can see my mouse here. So I'll say it again. Once this AB is done, you need to check AC. AC will be checked with this, and with this. Once this is done, then the next step would be to check for AD. AD will be checked with BA, CA, and DA, right? So given that the AC and AD are zeros, there is no need to check for them, okay? So simply put, we need to check AB, and you're going to find that AB is connected, AB is 1, and DA is 1, so DB would be 1, okay? So once this is done, you have a new one, this will be 1 now, right? So you have a new one, and now the next part would be do the same thing again. So this is what we're doing here. We will draw, let me just use a different color now. The second, we will use a second row. So this is R1. A second row, second column with the second row. Okay, we will repeat the same thing again. Okay, let me just delete the whole thing. So we will repeat the same thing again. We will start with AB, and here we will want to compare with this one. So if this was to be 1 here, if BA was 1 and AB was 1, AA would have been 1. So you take this one now, AB, and then you compare with BC, right? The row, you compare the row with the column 1, if you wish, whatever you want to call it. AB with BC, so it is 1 and 0, so nothing. Then you have AB and then BD. So I've compared AB with BA, and then I've checked AB with BC, nothing, still nothing, and then I've checked AB with BD. Now in this particular case, AB is 1 and BD is also 1. So technically, if you draw a line here, so this is AB and this is BD. Where they intersect at AD. So technically, oops, let me just erase all that, it would be much easier. So technically, with that being 1, just draw the so technically AD should be 1. Okay, so you're going to see in R squared AD has become 1. Okay, so there is a reason why you don't modify it in the same diagram, because if you modify in the same diagram, when it will be time to do R4, row 4, column 4, it may affect the whole thing. It will affect it in the next one, but the algorithm may get caught to that. So it will be amended in the next one. When you move to this one, right, it will be amended. So this will become 1. So technically, this will become 1. Let me just delete this one. I'm just going to, sorry about that. So this will become, I'm just going to put 1 here. So then we will compare. So AB is done. We're going to do CB now. CB, I'm just going to write it here. CB, you need to check CB with AB. CB and AB, you have nothing. CB with BC, sorry, this is BA, no? This is BA. With BC, nothing. CB with BD. In this one, CB is 0, BD is 1. Given that CB is already 0, there was no point of actually checking it, but I just did it for you to be able to understand it. Then we will try DB with AB. There is, sorry, BA. Then we will have DB with, given that BA is 0, DB with BC. This is 0. Then we will have DB with BD. And this is 1, this is 1. That means DD will have to be 1. So again, if you draw a dotted line on this side, and then you draw a dotted line on this side, you're going to see that it intersects here. So DD should be 1. So in the next iteration, given that I can use an eraser here, I'm deleting it, but this is what is happening here. Those two red modifications, this one and this one, will happen in the next one, okay? So we will be there in the next one, okay? So what I usually do is that when I'm doing for R1, I'm actually planning for, I'm already building R2, okay? What I usually do is that I draw R2. So what I usually do is that when you have a value, a change in value, let's suppose I was doing for AB and then BD, so I found a 1 here, so that would be 1. And later on, I find DD is equal to 1. Then I fill in the blanks for, this will be R2. So then this, I'll just fill in the blanks, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, and that would be 1, 1, 1, okay? So that would be R squared. Then the same process will be repeated again. So let's do the same process. So now it's going to be R3 row 3, R3 row 3. And simply put, just in this row, you can start with the column or the row, right? Or the column or the row here, whichever. So I'll start with the column here because I can see there is a 1 here. You don't need to check as such. You don't need to check for all elements because what you're interested, the moment you have a 1, you will see that you just need to check whether other elements has a 1 as well, okay? So you're going to see a 1 here and a 1 here. So I'm going to start with this one. So this one would be, this is A, B, C, D, A, B, C, D. So I'm going to check AC with CA. given that there is nothing here, it is 0, AC with CB. Then I'm going to check AC with CD. Given that there is no ones yet, it will remain unchanged. Then I'll repeat the same thing for DC. I'll check DC, this one, with CA. Then I'll check DC with CB. Then I'll check DC with CD. Given that there are no change, we can move on to the next part. So there will be no change. We can move on to R3. R3, there has been no change. So R3 being so the last column. Sorry about that. The last column and the last row. Remember, you have to show these rectangles, show the step-by-step how you're doing it, okay? So I'll start with this one. You have one here, one here. You could start with this one as well. It doesn't matter whether it's the row or the column, but I'll start with this one. AD. I'll check AD with DA. And given that AD is 1 and DA is 1, that means AA should be 1. So just compare these two, okay? AA should be 1. So in the next one, let me just delete this one. In R4, see what's going to happen in R4. In R, so that becomes R3. We're currently at R3. In R4, in R4, that would be 1 here. AA would be 1. Then we try AD with DB. And given that both are 1, AB should be 1. AD is already 1, so it will remain unchanged. Then we'll try the same thing, AD with DC. Then AC should be 1. AC is already 1, right? And this will remain unchanged. Then we try the same thing with B now. BD with BD with DB. So we tried, why am I doing this? BD with DA. So we do the same thing. And here we will check whether BA has something in there, then it's going to be BB. This will be B, and this will be B again. Right, so you can see that BD and DA, so BA should be 1. If you try the second one, BD, and then DB, so this being DB, then BB should be 1, so that becomes 1. Then if you try the third one, BD with DC, both of them are 1, that should be 1 as well. And that is already 1, okay? That remains unchanged. This these two, this one and this one, has remained unchanged. Okay, so then we move on to we start the same thing with, we could do the same thing for CD. We check with DA, with DB, and then DC. But given that CD is already 0, so that will remain unchanged. So that would be 0, 0, 0, 0. And the last one, given that we have already checked it, okay, we have already checked it with the rest of the column that we have here, column D. So this will remain unchanged as well, 1, 1, 1. So the transitive closure is this one, okay? 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1. This is what you can see here. Let me just do the same thing. I'll do the same thing one last time, just for you to be able to understand it clearly, okay? So let me just clear this. We'll repeat the same thing, okay? So what was the first one? So 0, 1, 0, 0, 0, 0, 1. 0, 0, 0, 0, 0, 1. You can do it at the same time, okay? Just for you to be able to understand it. And then 0, 0, 0, 1, 0, 1, 0. 0, 0, 1, 0, 1, 0. So that would be R0. And we will start the same process here. So for this one, why is this not going away? There we go. Right, so for this one, we will do the same thing. So we'll start with, oops. This is this one. So we start with row 1, column 1. So for R0 now, I'm just for R1, so this would lead to R1. R1 would be so we start with this one. We take the first one that we have, any one that has a 1 here, and we look in this one. We take the 1 here, and we look for anyone that has a 1 here. So if you have a 1 here, so I can keep right this one because this will remain unchanged, and this will remain unchanged as well. So given that I have a 1 here and a 1 here, this will have to be a 1 here. Okay, so I'm just going to highlight this. This will be a 1 here, and nothing else will change. So this will be 0, 0, 1, 0, 0, 0, and 1, 0. Right? So the next step would be, let's do the same thing for row 2 and column 2. Right? So row 2 and column 2, pretty simple. Let's do R squared. Sorry, the 1 should be there on the top. So let's do the same thing. So you're going to see that where this one, you need to check with this this, and this, okay, these three. Now you're going to see this one and this one, the first one and the second one, there is no difference. So you will see that if that is, just write it here, A, B, C, D, A, B, C, D, right? You're going to see that if you check AB and BA, BA, given that it is 0, it will remain unchanged. AB, if you're going to check with BC, BC is 0, it will remain unchanged. But AB and BD are both 1. So that, in this case here, will be 1, right? Similarly, if you're going to check DB with DD, sorry, DB, you check DB, so this one, with this one, right, BD, just, so DD should be 1. The rest are the same. So that would be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1. So we have R squared now. So the next step would be to check the third one. So this, obviously with practice, the more you practice, the easier it's going to get. So I don't have enough space, so I'm just going to put R cube here. So in this one, if you start with the row, you want to check this being AC. You're going to check AC with CA, AC with CB, AC with CD. But given that AC is already 0, BC is 0, everything is 0 in there except for DC, which is 1. But again, everything else is 0. Nothing will change in there because you have no 1, 1 that is connected in there. So this will remain the same, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1. So if you do this, now you need to check for the last row and the last column. 1 here and 1 here. So again, let me just do the up to the power 4 here. So in this one, you're going to see that AD and DA have both 1. So AA would be 1. AD and then DB are both 1. So that will be 1. Whether it's 1 or not, it will stay 1 if it's already 1. As if it's 0, it will be 1. AD and then DC are both 1. So AC would be 1, and the other one is already in the row there. Then we will try the second one, BD with DA, DB, and DC. Given that all of them are 1, this will be 1, 1, 1, and this is already 1. If you check the third one, given that it is 0, it will stay the same. It's already 0, and then the rest will stay the same. So this being the final answer, right? You can write the R closure. So it will have AA, AB, AC, AD, and then BA, BB, BC, BD, and then you're going to have DA, DB, DC, DD. Okay, so that's the answer. Okay, so that's how Warshall actually works. You have to show exactly the same steps that I've done. Usually what I actually ask students to do is simply highlight the changes. Like you can see, I've circled them, right? The changes. So here I've put it in green. You can just put a double mark under that just to note the changes that has occurred. Like for example, in this one, this has changed, this has changed, this has changed, this has changed, and this has changed, right? So you can't use, given in that in the exam or in the test, you can't use colors. You can simply just put an underline so that we know which one has changed. Is that okay, guys? I know it's not easy to understand, but I hope you did understand. Is it okay? Can I have a feedback, please? Okay, so can I have a feedback, please? In the chat, it's okay. Sorry, I'm just hidden this and I can't see it anymore. Just give me a second, please. I'm having an issue with my... There you go. Yes, can I have a feedback in the chat? Only 3 students have 8 students have replied. Okay, I hope it's okay, right? I can't make it any simpler on this one. I hope the rest of the students have understood it. Okay, so now we're having replies. Okay, good. So that's the Warshall algorithm. So obviously, what I've done in the slide is that I've actually, so this is the explanation. You don't have to learn this slide. This is not, this is later on in year 3 or maybe in year 2 if you're doing any project or anything you want to use implement the Warshall. This is the algorithm that you need to implement in your codes. Okay, so there will be 2 last questions, this one and this one, that you need to try for the Warshall. And you will see that later on we're posting a lot of exam questions pertaining Warshall. Okay, good. So let's jump to the other lecture now. Start the second one. If you want to take I mean, it's just the same thing. If you want to take a screenshot of this one, there you go. Explaining the Warshall, okay? So you need to go from R0 to R4, R4 being the final answer, okay? Allez. The next lecture is on functions and mapping. So my last lecture with you would be, so next week will be tests. Week after, we're going to do languages and then we are done, okay? And the other lecturer will take over with the next part. Okay? Right. Functions and mapping. Just give me a second. I'm totally dying. That should be better now. Okay, so functions and mapping. I've already done a little bit of introduction of functions and mapping. What you need to understand with function is that a function f from a set A to a set B is an assignment of exactly one element of B to each element of A. So there will be exactly one element of B to each element of A. So this is very important. We write f of A is equal to B if B is the unique element of B assigned to the function f, the element A being an element of the set A. If the f is a function from A to B, if f is a function from A to B, we write f semicolon f colon A and then the arrow B, which reads that f maps A to B. Now, somebody's microphone is on. Can you just turn it off? Every element, so this is the most important thing you really need to remember. To have a function, we need to have this condition satisfied all the time. Each and every element of A has a single mapping, right? So I'll explain in a few minutes. See if you have A here, and this will be the f of A. So if you have one element, each of them should be mapped on something here. If one of them is not mapped, then this is not a function, okay? Each element of A should be mapped, right, to every, has a single mapping. It needs to have, you cannot have this, right, going on onto something else, for example, okay? So each element of B can be mapped, right, by several elements of A. So each element of B can be mapped on this one and this one, for example, okay? So it can be mapped on several elements, for example, okay? So it's very important to understand these two components. Let me just explain that. So some terminologies, if A maps B, then A is the domain, B is the codomain, the element B is the image, and the element A is the pre-image, also known as the antecedent. And you're going to have a range. To explain this, let's visualize this. A maps B, right? Right? So A maps B. The left-hand side will be the domain, the right-hand side will be the codomain. B would be the image, the element B will be the image of the element A, right? So the element A would be the pre-image, and then whatever you're going to have, whatever elements from the set A, the domain, whatever is going to be mapped to from the codomain will be known as the range. Remember one thing, if you have a domain and a codomain, right? Let's say you have two elements in there, and here you have three elements, but these two are only mapping these two. The range will be this, not all of them, only those that are being mapped, okay? So this is just a visualization of the same thing. You can just go through that. So the pre-image, the image of 4.3 is 4. The pre-image of 4 is 4.3, okay? So move functions, you can have a class grade function. So everyone, somebody has Alice has an A, Chris has an A as well, Dave has an F, Emma has a D, okay? So the domain and the codomain, a string length function, same thing. You will see that, so some of the functions, example, how many times A has occurred, how many times E has occurred, how many times I has occurred, for example, and that would be the range. These are not given, they are part of the codomain, but they don't have a pre-image, okay? So same thing for this one. However, we have an issue for this one, okay? You can see that this is not a valid function, given that, right, it does not have a single mapping. The domain does not have the pre-image does not have a single mapping. It has a multiple mapping, okay? So another reason why it is not a function is because one of the pre-image that is from the domain is not mapped. So two reasons that this is not a valid function, okay? So function arithmetic, if you're doing addition of x is equal to x squared, so if you do f of x, f of 1 plus f of 2, it's simply 2x plus x squared, okay? If you do f of 1 multiplied by f of 2, then it's going to be 2x multiplied by x squared, which is going to be 2x cubed, okay? So basically, now we get into the gist of functions, and I'll need your full attention on this part. Let's give, so it's what time? Oh, 12:30, we'll stop it, okay? So the first function is what is known as a one-to-one. It's known as injective or injection, okay? We are looking at relationships between functions, just like we did on the previous chapter. So a function is a one-to-one if each element in the codomain has a unique pre-image, right? If each element in the codomain, that is the right-hand side, has a unique pre-image, meaning no two values map the same result. So you're going to see each element in the codomain, okay? So the codomain being on this side, each element of the codomain has a unique pre-image, this being the domain, which contains pre-image. So you're going to have pre-image, and the codomain will contain images, okay? So each of them, you can have a situation where it will still be on one-to-one. If one image, for example, 3, the image 3, is not mapped to a pre-image, okay? It's still a one-to-one, it's still injective, okay? This is not a one-to-one function because you can see that one of the image here, this one, has 2, it's still a function, right? But it has 2 pre-images, this one and this one. Remember we said it has a unique pre-image, okay? You should not have more than one pre-image, okay? So injective is synonymous to one by one. A function is injective, for example, or is an injection. So you can see that in a one-to-one, you can have unused elements in the codomain. So images may not be have a pre-image. So this is still possible. So in an injection, a function f is said to be a one-to-one or injective for all x and y in the domain of f, where f of x is equal to f of y. If f of x is equal to f of y, then x is equal to y. So it will be injective because all the domain should have a codomain. So x, that's why it says x is equal to y. Intuitively, an injection simply means that each element in the range has at most one pre-image, okay? So it may be useful to think that the contrapositive of this definition, so if you don't have this, this will not be equal to this. So we can conclude that x is always equal to y. So we can test this if you wish. So if you have a function, right, you can try this. Real on real, for example. I have another example here. So what we need to prove that f of x1 is equal to f of x2, right? This will show that it is an injection, okay? So if f of x1 is equal to x1 plus 5, f of x2 is equal to x2 plus 5, so that will simply mean x1 plus x5 is equal to x2 plus 5. x1, move 5 on the other side, you're going to see that it cancels. So we prove that x1 is equal to x2. So if this is equal, remember we said f of x is equal to f of y, then x is equal to y, then it is injective. So if we are able to prove this, then we say that a function is injective. Now, this function, this is the interesting part. It is not asking you whether it is injective on anything. It is asking you if you have real numbers, from real numbers to the real numbers. What does that mean? The domain is real, and the codomain is real as well. So whatever be if you're going, real numbers could be 1.3, could be minus 1.2, could be 3.6, for example, could be so many things. Whatever be the value that you're going to put in there, you will have the exact same value. You will have an injection on the other side. So if you put, let's say, minus 1.2 plus 5, that would be 3.8. So somewhere in the line, given that it is a real number, there will be 3.8. If you take 1.3 plus 5, that would be 6.8. So somewhere in the line, there will be 6.8. Right? So 3.6 plus 5, so that would be 8.6. Somewhere in the line, there will be 8. In the codomain, there will be 8.6. So you're going to see that some of them will not be marked. It should be marked, okay? All of them will be marked on this one because there will be a real number that marks this one, okay? So this is what we are actually trying to say here, okay? So similarly, you can also use a graph, okay? You can also use a graph to do that, but for linear equations, linear functions, it's very easy to do that. So, so when x is equal to 0, this will be 5. When x is equal to 1, this will be 6. So we can draw the line here. So that's f of x. Then you can show that in any values that you're going to have here, if this being a real number and this being a real number, you will have, for any values, you will have the corresponding value, okay? So this being x and this being y, okay? Or we'll call this one f of x, okay? So we can do the same thing for this one, this being f of x. Here I didn't ask for any real numbers or anything, so this being x, you can prove the same thing. It is injective because for any values of x, right, any domain, any pre-image, you're going to have a pre-image for it, okay? So you can use the same thing. But graph can be a little bit tricky. You cannot just, I've seen students just saying, they've just drawn a graph. This is f of x, 3x minus 2. They just draw the graph and then they simply think that the explanation is done. It can be very tricky. I prefer not to use graph in most cases because it's tricky to explain. Simply put, if it's an injective, you're looking at x is equal to y, or f of x is equal to f of y. So doing the same thing, f of x1 should be equal to f of x2. So f of x1 is 3x minus 2, and f of x2 is 3x minus 2. Simplify it, you're going to end to this. If you prove this equality, then therefore you need to conclude it is injective. Okay, or you can say it is a one-to-one. Okay, so we can try these questions if you wish. Let's try these questions and then we'll take a break. The first two are natural numbers. Just share in the chat whether part 1 is injective, part 2 is injective or not, part 3 is injective or not. Just make sure you have the slides in front of you. Okay, so let's go through the answer. It's very simple to explain this, okay? You have to be very careful when using graph, or also using, you could use um, f of x1 is equal to f of x2. But you remember, they are asking for the domain being neutral and the domain being, the codomain being neutral. So in this particular case, if you try to draw a graph, the graph would be, given that we're looking at, so f of x is equal to 5x here. sorry, f of x is equal to 5x. Given that we are looking at natural numbers, so natural numbers will be anything between 1 and it goes to, these are natural numbers, okay? So you're going to see that you can show that for 1, you will have 5 here. For 2, you will have 10 here. For 3, you will have 15 here, and it goes on like this. So this will be natural number, and this will natural number. Okay, so this is one way of proving it. So you can show that this is injective. For x squared, given that it is natural number, so I'm not going to draw this part because I don't want the negative one, okay? So I'm just drawing the positive part because natural numbers are positive numbers. So I'm going to have something like this. So that would be x squared, okay? So given that we are looking at natural numbers, okay? So this is the f of x, and this will be x. So for any element of natural number, 1, you will have a value here. So 1 here, 2 here, so that would be 4, and 3 here, and that would be 9. So you can give some example, just like I'm doing here. So that's going to be 16, and it goes on like this. So yes, this would be injective. For the third one, this is the interesting one. For the third one, how do you prove this? Again, you can use a graph if you wish. There are other means, measures as well. But for the third one, it's a little bit more intricate. Actually, it's not injective. Okay, I'll explain why. So if you do this curve here, so now, given that it's real numbers, right? So this would be f of x here, and this would be x. So we're looking at, sorry if I'm not able to draw it correctly, because I'm using this. Now, you're going to see one problem. Given that f of x should be real, just use a different color here. F of x should be real, and x, the domain, and the codomain should be real. So real numbers will have decimal numbers, for sure, and will have negative numbers, positive numbers, and so on and so forth. So for x, all the way here, right, should be catered, right? Good. So let me just draw this so that you can understand. So that's x, and the codomain would be f of x. So remember, this should be real numbers, and this should be real numbers. So by default, it already contains negative numbers up to positive, all positive real numbers. Same thing here, all negative numbers up to all positive numbers. By default, given that it is a real to real, it will contain all the possible numbers here. Now, the problem with this one is that when the domain, the pre-image is positive, you will have a value here, right? You'll have a value here. So there will be a value here. The other way around, whenever you have a negative value, you will have a value here. Okay? But the problem lies in this one. For these values, right, there will never be a value for this one, okay? There will never be a value for this one, okay? So let me just explain it. You're going to see that for negative values, when we're going to put, look here, for negative values, f of x here, for negative values here, you're not going to have an x1 is equal to x2, okay? It will not be a positive negative value. It will not be here. It will be somewhere here. So this is not injective, okay? So this is not a one-to-one, okay? Is that clear? If you look at the definition of one-to-one, meaning no two values mark the same result, okay? No two values, you cannot have, should mark the same one. Here, if you take, for example, for x squared, if you state 2 squared is equal to 4, so if I do it here, I will have 4 here, it will go to 2 squared, and minus 2 here will also go to 4, okay? So that's the problem with when you have real values, okay? Minus 2, so that should have been positive 2, minus 2, it will give the same outcome. Is that clear to everyone? Can I have an answer in the chat, please? You can replace by replacing x as well. Yes, you can see in the answer. You can show this problem here. For minus 2 squared, it's going to be 4. So you can conclude it is not a one-to-one because the value, the codomain, the image, in this particular case, the image is mapped. Sorry about that. Is mapped by more than one pre-image. So you can conclude this way. Is that okay? Good. Okay, let's take I forgot to give a break, quick break, 5 minutes, and then we move on to the last part of this section, next part of this section. Okay, so another type of relational functions are known as the onto function, the surjective. So remember, previously we were talking about a one-to-one. This is known as a surjective. A function is onto if each element in the codomain is an image of some preimage. So as opposed to the other one, a function is, meaning all elements in the right are mapped to. So here, all elements needs to be mapped to, okay? So this is, you can see all elements are mapped to a pre-image. You have an example here. You will see that this has not been mapped to. So this is not surjective. This function is not surjective, okay? So simply put, if it's mapped, all the image has a pre-image, one or more pre-images, then this is an onto function. In simple terms, this is surjective, okay? So a surjective function, a function is a surjection if it is onto. So note that there can be multiple used elements in the codomain. So you can see that the codomain, the element, the image 2 has two pre-images, I and O, okay? So let's have a look at this little question and let's figure out which one of them is injective and the other one is surjective, whether they are both or neither, okay? So let's do it together, okay? So for the first one, right, you will see that each image has one pre-image, okay? And there is one which is one image which is does not have any pre-image. So you can automatically see here, this cannot be an onto, but it can be a one-to-one, okay? So it is injective and it is not surjective. Why? Because surjective needs that all pre-image be assigned and all image be assigned a pre-image, okay? In this one, you will see that this is an interesting one. It is not a one-to-one. Why? Because you can see one pre-image here that has one image that has two pre-images here. So the image 2 has AD as pre-image. So that means it is not a one-to-one. It is not injective. However, it is surjective because all images are actually mapped by one or many pre-image. Let's have a look at this one. So you can see that all of them are mapped. All pre-image are mapped all image are mapped to a pre-image and vice versa. So it is both injective, and it is given that all the image have been used, it is also surjective. In this one, this is an interesting one. You will see that it cannot be surjective because one image is not being used. So, however, you're going to see that it is also not a one-to-one, simply because you can see that this one has two pre-image, okay? Is that okay? Okay. This one is not a valid function simply because this has two images. One pre-image has one pre-image, A has two images, okay? Good. Right, so let's try this question on surjective. let me show you how the working is being done for this one. It's not difficult to calculate this. So if you have shown that f of x plus 2 is surjective, again, you can use graph to do that, but you can also use, here you cannot check whether x1 is equal to f of x2. So you cannot do that. This is for injective. Here we're checking for surjective. So for all x being real numbers, so what you're going to check is that for all values of y, f of x, you will have, for all images, you're going to have a pre-image. So simply put, just say y is equal to f of x. So y is equal to 5x plus 2. Find y is equal to, find x, y is equal to, y minus 2 is equal to 5x. X is equal to y minus 2 divided by 5. So if you fill in some value, you're going to see, if you say, for example, y is equal to 0, right? X is actually a real number. If you put in y, so this being a real number, so this being real number, so this is y, so you have x, the domain, the codomain of x, the domain of x. I don't know why I'm not. So here, you will have all sorts of values. If you check any values here, right, you'll figure out that it will return you some kind of a value, okay? It will be marked somewhere in here. So if you check any of them, y is equal to 1, for example, it will return you 1 over 5 and so on and so forth. So you can check with a few values, you can actually check for any values of y or f of x from the domain. You can check if you have the value of x. If true, then it is surjective. Question number 7 would be, this one is for integers, right? So you can try it at home as a question. 8, homework. 9, homework. I'll explain bijection. I don't have enough time, so I'll explain bijection, and then in the tutorial, we'll come back to it, okay? What is bijection? If a function is both injective and surjective, we say that they are bijective, okay? So it is a bijection, okay? So you can see here, all image has exactly one pre-image, and you're going to see here, so it is a one-to-one, but it is also an onto because it has been assigned f of x is equal to f of y, okay? So in this case, we say it is a bijection. So you have a little question here. You can try it. Determine the type of each of these functions. So you need to say whether this is a homework. Please, I don't think it is in your slide. Can you just screenshot this, please? F of x is equal to 2 of x plus 1. So you need to determine whether it is a bijection or not, okay? Take a screenshot of this to complete the homework. Good? Right, so identity function, a function such that the image and the pre-image are always equal, right? So 1 multiplied by x for f of x is going to be the same thing. If x is equal to 1, f of x will be 1. If x is equal to 2, f of x will be equal to 2. And x plus 0, if x is equal to 0, f of x will be equal to 0. If x is equal to 2, f of x will be equal to 2. So the domain and the codomain must be the same set, okay? Right? So the inverse will be true as well. So so this will be the identity. The inverse of a function, if f of x is equal to 2x, okay? The inverse of x, the f inverse x would be x divided by 2, okay? So how do you know you have an inverse of the function? Okay. What is f inverse 2 here, not on 2, for example? How do you know? You will have this sentence is very important. The only situation where an inverse of a function is possible is when it is bijective. That is, it is both injective and surjective. Surjective. Okay? If it is a bijective, it is a bijection, then for sure it will have an inverse. Okay? So you have a bunch of questions. Find the inverse of this one. Okay? These are simple questions. You don't need to prove anything. But to know whether it has an inverse, you need to prove whether it is bijective. If it is bijective, there will be an inverse. Okay? Same thing. You can try these questions at home. On real numbers, from real to real, the domain being that. Function composition, what is that? Let G be a function such that A maps B, and F be a function such that B maps C, right? So F circle, we're looking at function composition G of X, will simply say F of G of X, right? This is what is known as function composition. Let me just explain it. If f of x is equal to 2x and g of x is equal to 3x, right? F of gx, for example, would be 2 into 3x plus 2 plus 3. Remember, f of x is 2x plus 3. So this will be fitted here. Okay, so this is f of x gx. F of gx, sorry. Okay, so if f of x, if gx, when x is equal to 1, when x is equal to 1, if you fit 1 in there, so g1, this will return you 5. If you have 5 here, this will return you f of x is equal to 5 here. This will return you 2 times 5 plus 3. This will return you 13. So this is what is being done here. Okay, so just explaining the same thing. Okay, just some animation to show that. Okay. Now, the big question is, does f of gx is equal to g of fx, right? So let's figure out. They are not equal. Okay, you have to be very careful about that. Okay, function composition is not commutative. Okay, so you have a bunch of questions. You can try those. You can try those at home. You can, as I said earlier on, you can use graphs for functions. You've done it before. You can show that using graph. And the last element that we're going to show here is useful functions. So this being x, and you see this symbol here, this means the floor, this means the seal. So round is equal to the floor plus 0.5. So a little example here, the floor of this one would be 1. The seal of 1.1 would be 2. The floor of minus 0.1 would be minus 1. The seal of 0. minus 1 would be 0. The seal of 2.99 would be 3. The seal of minus 2.99 is minus 2, and so on and so forth. So you're going to have a bunch of questions where you see that find f of s if these are the values. Okay, so you need to find the seal of these functions. Okay, so that's it for today. I'm just going to stop it there, guys. I'm just going to, please do all the homeworks. We'll take it in the, I'm sure you will have lots of questions. I'll take it in the tutorial. We're going to go through all of them. Remember, this week's tutorial, we're not going to correct it. Maybe next week. This week's tutorial, we're going to have a mock test. However, if you've already done these questions, I would advise you to complete those questions before Wednesday. If there is anything you want me to explain again, I can just go through it. Given that we've just completed the class, maybe you have some doubts, I will help you out. Right? On this note, I will wish you best of luck for the mock test on Wednesday. Please be present for the mock test. And it will be around 55 minutes, and will take 5 minutes to give you the answer, and maybe later on you can start correction. Please don't be late in the tutorial, else it will cascade on the other sessions. Okay. If you wish, exceptionally for this tutorial, if you wish to combine, for those students who feel that they want to join, given that it's going to be a common mock test, for those of you who don't have parallel session, you can join early tutorials. Like for those of you who wants to join the first tutorial 8:30 to 10:30 to 9:30, you can join that. So those of you in the last batch, if you want to join an earlier tutorial for this week, exceptionally, it will be allowed. Okay. So I repeat it again. For tomorrow's Wednesday's tutorial, you can merge in other tutorials, earlier tutorials. Okay. So batch D, if you wish to, not batch D, but the last batch, the one that starts at 12:30 and ends at 1:30, you can join another tutorial. Okay, provided we have seats in the tutorial. Is that okay? Take care, guys. I'll stop it from here. See you on Monday.